Have you ever wondered what really sits on the side of the moon we never see for most of human history? The far side was only an assumption, blurred images, rough models, and the belief that it must simply mirror the front. But when spacecraft finally reached it, the surface didn't match our expectations. The crust is thicker. The chemistry shifts in surprising ways. And the scars in the rock trace a history different from the moon we know. If this kind of quiet discovery feels right to you, like and subscribe to the video. Now, let's begin. On August 23rd, 2023, the history of space exploration turned a new page. India successfully guided the Chandrayaan-3 spacecraft to a soft landing on the surface of the moon. This was not merely another arrival on our celestial neighbor. It was a precision landing in one of the most hostile and challenging environments in the solar system, the lunar South Pole. This region has remained largely hidden from our view on Earth, shrouded in deep shadows and rugged terrain. To the untrained eye, it might appear as just another stretch of gray craters and silence. But to the scientific community, this specific location is a treasure chest waiting to be opened. The prize hidden within these shadows is lunar ice. For decades, we looked at the moon and saw dry, desolate rock. However, recent data suggests that the South Pole is far more abundant in frozen water than the northern regions or the equatorial plains we explored in the 20th century. The excitement driving this research is well-founded. This ice is not just a geological curiosity. It represents a fundamental resource for the future of humanity. It is a frozen reservoir of water, and water is the primary constraint on our ability to explore deep space. If we can harvest this ice, it could serve as the foundation for a permanent lunar settlement beyond habitation. This water has a more volatile potential. It can be transformed into fuel for missions destined for Mars and beyond. The knowledge of this ice is not entirely new. Scientists have suspected its presence for over 2 decades, following data returned by NASA spacecraft that accidentally detected hydrogen signatures, a telltale sign of water, while orbiting the moon. The confirmation solidified in 2018, when NASA stated with absolute certainty that water ice exists on the surface at the South Pole. This declaration changed the calculus of space travel. Imagine a future where lunar settlers do not need to rely on supply ships from Earth for every drop of water they drink. By tapping into these local reservoirs, they could sustain agriculture and life support systems in the barren lunar landscape. Furthermore, the chemistry of water offers a powerful utility. By using electricity to split water molecules, a process known as electrolysis, we can separate the oxygen atoms from the hydrogen. The oxygen provides breathable air, while the liquid hydrogen and liquid oxygen combination creates one of the most efficient rocket propellants known to physics. Developing this infrastructure would make lunar missions self-sustaining and significantly more feasible economically. Instead of lifting heavy fuel from Earth's deep gravity well, we could refuel in orbit. But the ice holds value beyond its utility. It is also a time capsule. Because the moon lacks geological activity like plate tectonics or wind erosion, this ice may have remained undisturbed for billions of years. Studying its isotopic composition could unlock deep mysteries about the formation of the moon and the early history of Earth itself. This leads to a broader realization. Water is not unique to our home planet. It is actually quite common across the cosmos. We have begun to detect signatures of water vapor in the atmospheres of planets orbiting distant stars. Remarkably, the chemical signature of this distant water is often identical to the water found in our own solar system. This points to a profound conclusion about our origins. The water that fills Earth's oceans likely came from space. The process begins in the vast, swirling clouds of gas and dust around newborn stars. In these stellar nurseries, water forms as a hot vapor. As the system cools, this vapor transitions directly into ice, coating tiny dust particles in a layer of frost. Over millions of years, gravity does its work. These icy dust grains collide and stick together, slowly building up into larger bodies, pebbles, boulders, and eventually, comets and planets. This mechanism suggests that water is a universal constant, spread across the galaxy by the physics of star formation. In our own solar system, comets and icy asteroids acted as delivery vessels. Scientists believe that eons ago, during a chaotic period of bombardment, these water-rich objects crashed into the lunar surface and the young Earth, depositing the water we see today. On the Moon, most of that water evaporated into space, except for the molecules that landed in the deep, permanent shadows of the polar craters. There, protected from the sun, they have remained frozen for eternity. This geological history has immediate implications for us today. The South Pole is now considered the ideal canvas for humanity to establish its first extraterrestrial foothold. The vision is no longer science fiction. We can imagine a network of structures, perhaps brick domes reinforced with lunar soil, connected by secure underground tunnels to protect against radiation. These bases would be hives of activity, with scientists and engineers monitoring systems, analyzing samples, and managing the complex logistics of a functional colony. Outside, the landscape would be traversed by pressurized rovers, carrying crews to mining sites where they would extract the precious ice and other minerals. Constructing this reality requires a shift in engineering philosophy. The traditional approach to space travel involves building everything on Earth and launching it atop massive rockets. This is incredibly expensive and limits the size of what we can build. A more effective strategy is to look at our history as a species. When humans explored new continents, we did not carry all our timber and stone with us. We surveyed the surroundings, identified available resources, and used them to build shelter and tools. This concept, known as in-situ resource utilization, is how we spread across Earth. And it is how we will spread across the Moon. The question then becomes, what can a desolate rock offer us? We know about the ice, but the Moon offers two other critical resources: minerals and sunlight. The lighting conditions at the lunar poles are unique in the solar system, unlike the Earth or the lunar equator, where day and night cycle relatively quickly. The poles experience a different phenomenon because the Moon's tilt is very slight relative to the Sun. There are peaks at the South Pole where the Sun hovers near the horizon for extended periods. These peaks of eternal light offer an almost uninterrupted source of solar power. Imagine a location bathed in perpetual sunlight, where solar arrays can generate electricity continuously without the need for massive battery banks to survive a 2-week lunar night. We can harness not just the light, but the heat. In a place where resources are scarce, efficiency is paramount. If we produce oxygen as a primary product, we will be left with metals as a byproduct. We must find a purpose for that metal. Responsible stewardship of the environment should begin on the Moon, minimizing waste and maximizing utility. This philosophy extends to the ground beneath our feet. The lunar surface is covered in a layer of fine data, gray dust and rock fragments called regolith. Scientists are currently developing methods to transform this abundant dust into sturdy building materials. The techniques are inventive. One approach involves using the concentrated heat of the sun, or lasers, to melt lunar dust layer by layer. This is essentially a massive, slow-moving three-dimensional printer that uses the moon itself as ink. Engineers have also successfully created bricks by cooking simulated lunar soil in solar ovens or fusing it with microwaves. The results are promising. The regolith, once fused, forms a ceramic-like material that is incredibly hard and durable. It is entirely possible that the first permanent structures on the moon will be built from these moon bricks. Manufactured in small, automated factories on the surface, it evokes the simplicity of building with blocks. But the application is critical. These bricks could be used to construct landing pads, roads, and protective shells over inflatable habitats, shielding astronauts from the harsh environment. This construction will likely not be done by hand. We cannot expect astronauts to perform heavy labor in pressurized suits. Instead, we will rely on automation. We will need to deploy systems of collaborative robots, swarms of machines that can excavate, and print structures autonomously. Humans will act as overseers, managing the construction site from the safety of a lander or even from Earth, despite the heavy reliance on robotics. The goal is to create a habitat that is livable for humans. Architects are already designing interiors that maximize space in stacked modules, creating multi-purpose areas that feel less like a tin can and more like a home. However, we must remain realistic about the challenges. The moon is an extreme environment. Without an atmosphere to moderate temperature, the surface swings wildly between extremes. In direct sunlight, temperatures can soar to 212 degrees Fahrenheit. Yet, just a few feet away, in a shadow, the temperature can plunge to minus 290 degrees Fahrenheit. This thermal shock puts immense stress on materials, causing them to expand and contract, which can lead to structural fatigue over time. Beyond the temperature, the moon is bombarded by solar radiation, cosmic rays, and micrometeorites, tiny particles of rock moving at bullet-like speeds. Then, there is the dust. Lunar dust is unlike anything on Earth. On our planet, wind and water erode sand grains until they are round and smooth. On the moon, there is no erosion. The dust particles are jagged, sharp shards of glass and rock created by meteorite impacts. Furthermore, the dust is electrically charged by solar radiation, making it cling to everything: spacesuits, visors, and machinery. It is difficult to remove and highly abrasive. During the Apollo missions, astronauts reported that the dust clogged joint mechanisms and wore through layers of their boots. Inside the habitat, it poses a health risk. The particles are so fine they can be inhaled, potentially causing respiratory issues similar to silicosis. It caused what astronauts called lunar hay fever, with symptoms of sneezing and watery eyes. Controlling this toxic, clinging dust is one of the primary engineering hurdles we must clear before long-term habitation is possible. Yet, the scientific rewards outweigh the risks. The far side of the moon and the polar regions offer a quietness that does not exist on Earth. Scientists are eager to utilize this silence to study low-frequency electromagnetic waves. These waves are the faint whispers from the early universe, signals that have traveled for billions of years. On Earth, our ionosphere blocks these frequencies, and our own radio transmissions drown them out. But the Moon acts as a massive shield by placing radio telescopes on the far side, shielded from Earth's noise. We can record these elusive signals. This data could allow us to peer back into the cosmic dark ages, the time before the first stars ignited, helping us understand the very origins of the universe. Recognizing these opportunities, NASA has established the Artemis program, a comprehensive roadmap for returning to the Moon. The first step, the Artemis 1 mission, successfully sent an uncrewed capsule around the Moon and back. Splashing down in December 2022, it proved that our new generation of rockets and heat shields can survive the journey. The goal is to establish a sustained presence, not just a series of brief visits. A key component of this plan is the Gateway, a space station that will orbit the Moon, serving as a staging point for astronauts descending to the surface. The timeline is ambitious. Artemis 2 is scheduled to carry a crew around the Moon in 2024. Following that, Artemis 3 aims to land 2 astronauts near the South Pole in the mid-2020s. If these missions succeed, we could see the foundations of a lunar base within the next 2 decades. The momentum is building, fueled by new discoveries. India's mission recently detected the presence of sulfur in the soil near the South Pole. This might seem like a minor detail, but in the world of construction, it is significant. Sulfur can be used to make sulfur concrete, a building material that requires no water to mix, a crucial advantage in a water-scarce environment. The presence of sulfur also provides clues about the Moon's volcanic past, suggesting that this quiet, gray world was once a place of fire and geologic fury. The detection of sulfur was a significant milestone, but it was only one piece of a much larger puzzle being assembled in real time. Less than a week after the Chandrayaan-3 lander touched down at a latitude of approximately 70 degrees south, its rover began transmitting data that confirmed the presence of this unexpected chemical element. The date was August 23rd, 2023. This was not just a successful landing, it was a precision arrival in a region that had never been explored on the surface. India became the 4th nation in history to achieve a soft lunar landing. But remarkably, it was the first to do so this close to the southern polar region. The strategic value of this location cannot be overstated. We are drawn here not by the scenery, but by the potential hidden within the regolith water ice. If the orbital data is correct, and this ice exists in extractable quantities, the implications are revolutionary. It transforms the Moon from a remote scientific outpost into a fueling station for the solar system. This ice is the raw material for drinking water, oxygen, and liquid hydrogen rocket fuel. To verify this potential, the solar-powered Pragyan rover embarked on a 2-week sprint against time, racing to collect data before the sun set and the brutal lunar night began. While the rover hunted for chemical signatures, the lander itself performed a maneuver that surprised many observers. On September 3rd, towards the end of its operational life, the spacecraft fired its engines again. This was not a launch home, but a hop. The lander lifted itself approximately 16 inches off the surface, and touch down again roughly 12 to 16 inches away. To a casual observer, a 16-inch hop might seem trivial. However, in the context of aerospace engineering, it is a demonstration of critical capability. It proved that a spacecraft, after sitting in the harsh lunar environment, could successfully restart its propulsion systems and lift off. This technology is the cornerstone of future human exploration. If we are to send astronauts to the moon and bring them back, or launch soil samples to Earth, we need absolute confidence that engines will fire on command after days or weeks on the dusty surface. As the mission progressed, the data began to challenge our pre-existing models. One of the most immediate surprises came from a simple temperature probe. The lander deployed a thermal probe capable of measuring the temperature of the topsoil at various depths. Based on orbital models, scientists expected the surface temperature in this region to be moderate, hovering between 68 and 86 degrees Fahrenheit. The reality was starkly different. The sensors recorded surface temperatures around 158 degrees Fahrenheit. This is significantly hotter than anticipated, suggesting that the thermal properties of the lunar soil at the pole, specifically how it absorbs and retains solar heat, are different from what we understood. It forces us to recalibrate our thermal models for future habitats and equipment. Beneath the surface, the chemistry proved equally rich, beyond the sulfur. The mission's instruments confirmed a cocktail of elements essential for construction and industry: aluminum, calcium, iron, titanium, and silicon. These are the building blocks of modern civilization, sitting there in the dust, waiting to be used. But the rover did not just look at the chemistry, it listened to the ground, using a specialized instrument designed to detect lunar seismic activity. It recorded vibrations, rumbles, and quakes beneath the surface. These moonquakes are vital clues. On Earth, earthquakes help us map the planet's core and mantle. On the moon, these tremors help us understand the internal structure and whether the geological heart of the moon is truly dead or if it still holds residual heat. This brings us back to the sulfur. Its presence is a geological riddle. Sulfur is typically associated with volcanic activity. Its detection raises a compelling question. Was this sulfur formed by ancient volcanoes erupting on the moon billions of years ago? Or was it delivered more recently by the impact of a meteorite? To answer this, we have to look at how rocks travel through space. And sometimes, the journey is reversed, in a twist that blurs the line between Earth and Moon. One of the most fascinating lunar rocks ever analyzed might actually be an immigrant from Earth. Among the hundreds of pounds of rock brought back by the Apollo 14 astronauts, scientists found a small fragment, a chip only 0.7 inches wide, embedded inside a larger breccia rock. Chemical analysis revealed that this fragment crystallized about 4 billion years ago, but not in a lunar environment. It formed at temperatures and pressures that correspond to a depth of about 12 miles beneath the surface of the Earth. Furthermore, it formed in the presence of water, an environment that existed on early Earth, not the moon. This tiny stone tells a violent story of our planet's youth. 4 billion years ago, the solar system was a shooting gallery. A massive asteroid likely slammed into the Earth, blasting debris high into the atmosphere. At that time, the moon was much closer to us, about 3 times closer than it is today. This proximity made it a larger target for escaping debris. The terrestrial rock was ejected into space, crossed the gap, and slammed into the lunar surface. Over eons, it was buried, crushed, and fused into a larger lunar rock by subsequent impacts, only to be picked up by an astronaut billions of years later. It is the oldest known Earth rock, and it survived only because it left Earth on our planet. Plate tectonics and erosion have erased almost all rocks from that era. To find our own origins, we had to go to the moon. The exploration of the moon's hidden history took another leap forward in 2019 with China's Chang'e 4 mission. This was the first spacecraft to ever land on the far side of the moon, the hemisphere that permanently faces away from Earth. This isolation creates a unique radio-quiet environment. But it also means the terrain is rugged and less understood. The mission's Yutu-2 rover was equipped with ground-penetrating radar, a technology that allowed it to see beneath the dust. The radar images revealed a layered history extending nearly 1,000 feet down. The top 130 feet are composed of loose dust, soil, and broken rocks, the ejecta from billions of years of meteorite impacts. But deeper down, the story changes. The radar detected layers of ancient lava flows, evidence of a time when the moon was volcanically active. Interestingly, the data showed that the volcanic rock layers became thinner the closer they were to the surface. This pattern tells us about the moon's dying breath. It suggests that volcanic eruptions were massive and frequent in the distant past. But over time, as the moon's interior cooled, the eruptions became smaller, weaker, and less frequent, until they stopped altogether. The moon has been geologically quiet for perhaps 1 billion years, but its violent youth is frozen in these layers. However, the most dramatic scar on the moon is one we can barely see from Earth. It is the South Pole Aitken Basin. This is not just a crater, it is a colossal impact basin, one of the largest and oldest in the entire solar system. It stretches more than 1,500 miles in diameter and digs 5 miles deep into the lunar crust. It covers nearly a quarter of the moon's surface. From Earth, we only see the mountains of its outer rim peeking over the edge, silhouetted against space. Astronomers believe this basin was formed around 4 billion years ago by a cataclysmic impact with a large asteroid. But the impactor left behind more than just a hole. Buried beneath the floor of the basin, roughly 180 miles underground, lies a mysterious, massive anomaly. It is a chunk of high-density material with a mass roughly equivalent to 1,000,000,000 tons, that is a number with 18 zeros. To visualize it, imagine a pile of metal 5 times the size of the big island of Hawaii buried underground. This anomaly was discovered by NASA's GRAIL mission, the Gravity Recovery and Interior Laboratory. The GRAIL spacecraft orbited the moon in tandem, measuring minute changes in the moon's gravitational pull. When they flew over the South Pole Aitken Basin, they detected a significant increase in gravity, indicating that something incredibly heavy was pulling down from beneath the surface. What is it? There are 2 leading theories. One suggests it is a dense concentration of oxides that formed when the moon was still a molten ocean of magma. As the magma ocean cooled and solidified, heavy minerals might have settled and concentrated in this region. However, the more favored theory is far more dramatic. Most scientists believe this mass is the metallic core of the giant asteroid that created the basin. When the asteroid struck, it didn't just bounce off, it penetrated deep into the moon's crust. The heat of the impact kept the core molten, and it remained suspended in the moon's mantle rather than sinking to the core. It is a ghost of the collision, a metallic heart still beating with gravitational weight beneath the scars of the impact. While we investigate these solid masses, other researchers are looking for empty spaces. There is growing evidence that the moon is riddled with a labyrinth of underground tunnels known as lava tubes. These structures form during volcanic eruptions when rivers of lava flow across the surface. The top layer of the lava stream cools and hardens into a solid crust, insulating the molten rock beneath. When the eruption ends and the lava drains away, it leaves behind a hollow, tunnel-like cave. NASA's Lunar Reconnaissance Orbiter has photographed numerous skylights deep, dark pits on the lunar surface that appear to be collapsed roof sections of these tubes. Recent gravity data supports the existence of massive voids beneath these pits. These lava tubes are not just geological curiosities, they are potential habitats. Inside a lava tube, astronauts would be naturally shielded from cosmic radiation, micrometeoritis, and the wild temperature swings of the surface. The temperature inside these caves is believed to be a stable 63 degrees Fahrenheit, remarkably mild compared to the surface extremes. If these tubes are accessible, they could house entire cities, protected by the moon's own crust. But perhaps the most unexpected discovery relates to a material we usually associate with kitchen renovations: granite. In July 2023, scientists announced the discovery of a massive formation of granite beneath the lunar surface at a location called the Compton-Belkovich Volcanic Complex on the far side. This was shocking because granite is incredibly rare in the solar system outside of Earth. On our planet, granite forms when water-rich oceanic plates are pushed under continents and melt, a process driven by plate tectonics and abundant water. The moon has neither plate tectonics nor liquid water oceans. Yet, there it is. Scientists detected it by measuring heat. Granite contains higher concentrations of radioactive elements like uranium and thorium compared to other rocks. These elements decay and release heat using microwave radiometers on Chinese orbiters. Researchers found a hotspot about 31 miles across that was roughly 18 degrees Fahrenheit warmer than the surrounding terrain. This thermal signature matches that of a large granite batholith, a solidified magma chamber buried underground. This discovery forces us to rewrite the textbooks. It implies that the moon, in its early history, had a much more complex geological evolution than we thought. It suggests there were mechanisms to concentrate magma and perhaps even significant amounts of water involved in the crust's formation that we have yet to fully understand. This granite formation, similar to the iconic cliffs of El Capitan in Yosemite, stands as a silent testament to a time when the moon was geologically alive, churning and evolving in ways that mirrored our own Earth. The discovery of granite on the far side of the moon is more than just a geological footnote. It is a fundamental challenge to our understanding of planetary formation. On Earth, we take granite for granted. We use it for countertops, monuments, and heavy construction. Its ubiquity is a direct result of our planet's unique machinery, plate tectonics, and liquid water. When oceanic crust, saturated with water, dives beneath a continent, it melts. This hydrous magma rises, cools slowly, and crystallizes into the granite we see in mountains like the Sierra Nevada. It is a process inextricably linked to water. Yet, the moon has neither tectonic plates nor oceans. It is a dead, dry world. Finding a massive granite batholith there is like finding a coral reef in the middle of the Sahara Desert. It shouldn't exist according to our standard models. This paradox suggests that the early moon was a far more dynamic and perhaps wetter place than we ever imagined. It implies that localized pockets of water or extreme magmatic differentiation occurred in the ancient past. Driven by volcanic engines, we are only just beginning to map. While we wait for future samples to solve this riddle, the very presence of this rock proves that the moon is not a simple, monolithic block of basalt. It is a complex, evolved world with a history that rivals the Earth's in its violence and variety. This brings us back to the central question of lunar exploration water. The relationship between science and lunar water has been a centuries-long roller coaster of optimism and disappointment. In the mid-17th century, when telescopes were first turned skyward, astronomers like Michael van Langren looked at the dark, smooth patches on the moon and called them Maria, the Latin word for seas. They imagined vast oceans of liquid water. By 1892, that romantic notion was crushed. American astronomer William Pickering correctly deduced that the moon had virtually no atmosphere. Without air pressure, liquid water cannot exist. It would instantly boil away into the vacuum. The scientific consensus shifted to the other extreme. The moon was bone dry, drier than any desert on Earth. For nearly 70 years, this dogma held firm. Then, in the 1960s, a physicist named Kenneth Watson proposed a radical idea. He suggested that while liquid water was impossible, ice could survive. He theorized the existence of permanently shadowed regions, deep craters at the lunar poles where sunlight never reaches the bottom. In these eternal shadows, temperatures would remain low enough to act as cold traps, preserving water ice for billions of years. It was a brilliant theory. But when the Apollo astronauts returned with dust, dry soil samples from the equatorial regions, the idea of a wet moon was shelved again. It wasn't until the turn of the millennium that technology caught up with theory. The Clementine mission in 1994 and the Lunar Prospector in 1998 detected hydrogen signatures at the poles, reviving the hope of ice. But the definitive proof came recently, in 2020. NASA's SOFIA Observatory, a telescope mounted inside a Boeing 747, detected the precise chemical fingerprint of H2O on the sunlit surface of the moon. This was a game changer. It meant water wasn't just hiding in dark craters. Molecules of water were actually clinging to grains of lunar dust, surviving the harsh solar glare. This confirmation recontextualized everything, including the Apollo samples. When scientists re-examined those 50-year-old rocks with modern instruments, they found tiny traces of water trapped inside glass beads, evidence that had been overlooked for decades. The moon, it turns out, has been holding on to its water all along. But water is not the only resource that makes the moon an attractive destination. The regolith, the layer of dust and broken rock covering the surface, is a chemistry set waiting to be used. Beyond silicon and oxygen, the lunar highlands are rich in calcium. This is not just for building strong bones. In the vacuum of space, pure calcium metal becomes a highly efficient electrical conductor. It could replace copper in lunar power grids. Furthermore, the mineral anorthite, which is abundant in these highlands, contains the necessary ingredients: calcium, aluminum, and silicon to manufacture solar panels directly on the lunar surface. We could essentially scoop up the dirt and bake it into energy-producing cells. Then, there are the precious metals. In 2009, NASA's L-Cross mission deliberately crashed a rocket stage into a crater near the South Pole to see what would fly up. The resulting plume was analyzed by a trailing spacecraft, The data was a revelation. It detected a cocktail of volatiles: carbon monoxide, ammonia, sodium, and surprisingly, trace amounts of silver and gold. While the concentrations are low, their presence confirms that the heavy bombardment of the early solar system salted the moon with heavy metals. This leads to a fascinating economic prospect: the moon rush. The moon's surface is pockmarked with over 1.3 million craters larger than a kilometer. But for prospectors, the interest lies in the roughly 6,500 large craters. These are the scars left by massive metallic asteroids. On Earth, when a heavy metallic asteroid hits, the precious metals platinum, palladium, iridium often sink deep into the crust or are eroded away by wind and rain. On the moon, there is no erosion. The shattered remains of those asteroid impactors, potentially worth trillions of dollars, are still sitting there, mixed into the dust just a few feet below the surface, because the moon lacks an active geology to recycle its crust. It acts as a museum of the solar system's history. Most of the mineable gold on Earth is thought to have arrived via asteroid impacts after the planet's crust formed. The moon received that same bombardment. The difference is accessibility. Mining on Earth often requires drilling miles deep. On the moon, the ore might be sitting in a pile of rubble in the center of a crater. However, a colony cannot survive on gold and platinum alone. It needs food. This raises the critical question: can we farm on the moon for 50 years? The answer was a theoretical maybe. Then, recently, researchers at the University of Florida decided to find out for real. NASA granted them a loan of just 12 grams of pristine lunar soil, collected during the Apollo missions, a teaspoon of some of the rarest material on Earth. The team planted seeds of Arabidopsis thaliana, a small flowering plant related to mustard greens, directly into the lunar regolith. To the amazement of the scientific community, they sprouted for the first time in history. Terrestrial life grew in alien soil, but the victory was bittersweet. The plants were stunted and stressed. They grew slowly, and their genetic expression showed signs of fighting a harsh environment. The lunar soil is not like Earth soil. It is sharp, abrasive, and lacks the organic nutrients and bacteria that plants co-evolved with. It is essentially crushed glass. While the experiment proved that lunar farming is possible, it also showed that we cannot just plant seeds and wait for a harvest. We will need to engineer lunar fertilizer, perhaps composting our own biological waste, or mixing in additives brought from Earth, to turn the sharp regolith into a nurturing soil. Despite the challenges, the vision of a lunar economy is coalescing. It is a vision where we do not just visit, but stay. We mine the craters for platinum to build electronics. We harvest the polar ice to brew oxygen for breathing and hydrogen for fuel. We use the calcium and silicon in the dust to build solar farms and habitats. And inside those habitats, we tend to gardens growing in modified moon dirt. This concept of in-situ resource utilization, living off the land, changes the moon from a final destination into a gateway. If we can refuel ships in lunar orbit using propellant manufactured from lunar ice, the cost of traveling to Mars drops dramatically. The moon becomes a gas station on the interplanetary highway. It becomes a training ground where we perfect the technologies of off-world living: radiation shielding, dust mitigation, and closed-loop life support. Private companies are already maneuvering to be part of this future. Startups are designing spacecraft to prospect asteroids, while major space agencies are collaborating on the Artemis Accords to establish the legal and logistical framework for lunar utilization. The idea of humans and robots working side by side on the gray peaks of the South Pole is no longer science fiction. It is a schedule. But as we stand on the precipice of this new era, we must acknowledge the sheer difficulty of the task. The vacuum is unforgiving. The radiation is invisible and deadly. The dust is a mechanical nightmare, and the logistical chain from Earth is fragile. Yet, the potential reward, a multi-planetary civilization anchored by a thriving industrial base on our nearest neighbor, is enough to drive us forward. The moon is not just a rock in the sky. It is the 8th continent, waiting to be settled. As we stand on the brink of this new industrial era in space, we are forced to confront questions that are as much about philosophy and law as they are about engineering. The rush to mine the moon inevitably draws parallels to the gold rush of the American West, a chaotic scramble for wealth in a land where the rules were written in pencil, if they were written at all. Currently, the governance of celestial bodies relies on the Outer Space Treaty of 1967. This document, crafted during the height of the Cold War, states explicitly that no nation can claim sovereignty over the moon. No flag planted in the dust equals ownership of the land beneath it. However, the treaty is notoriously vague regarding the actions of private entities and the extraction of resources. It does not explicitly forbid a private company from landing a robot, mining a ton of platinum, and selling it. This legal gray area creates a finders keepers dynamic. If a corporation invests billions to build the infrastructure, do they own the ore they extract? The international community is currently in a race to define these rules before the first commercial excavators touch down, aiming to prevent a lunar free-for-all where strategic craters are contested like terrestrial oil fields. The stakes are higher than just profit. There is a profound concern regarding the preservation of the moon's unique environment. To an astronomer, the far side of the moon is the most valuable real estate in the solar system. Not for mining, but for silence, shielded from the radio chatter of Earth by 2,000 miles of rock. It is the only place where we can build radio telescopes to listen to the faintest signals from the early universe without interference. Industrial mining operations, with their heavy machinery and communications arrays, would destroy this radio silence. Furthermore, mining creates dust in the low gravity of the moon. Dust kicked up by excavation can hang for huge distances, potentially coating delicate sensors and ruining billion-dollar scientific experiments. This conflict of interest between those who want to exploit the moon and those who want to study it has led to proposals for planetary parks. These would be protected zones, similar to national parks on Earth, surrounding historically significant sites like the Apollo landing zones or scientifically critical areas like the deep polar craters. The goal is to balance the economic imperative of resource extraction with the duty to protect the moon's scientific and cultural heritage. But for the average person on Earth, the question remains, why does this matter? The answer lies in the trickle-down effect of technology and energy. The rare metals sought on the moon, platinum, palladium, rhodium, are critical components in modern technology, used in everything from catalytic converters and medical electronics to hydrogen fuel cells. An influx of these materials could lower the cost of high-tech goods and accelerate the transition to green energy. However, the holy grail of lunar mining is a substance called helium-3. On Earth, helium-3 is incredibly rare. On the Moon, it is abundant. Deposited in the soil by billions of years of solar wind bombardment, scientists believe this isotope could be the key to unlocking commercial nuclear fusion, unlike current nuclear power, which splits heavy atoms and creates radioactive waste. Fusion merges light atoms to release energy. A fusion reactor powered by helium-3 would be highly efficient. Crucially, would not produce dangerous neutron radiation or long-lived radioactive waste. In theory, a single space shuttle cargo bay full of helium-3 could power the entire United States for a year. It offers a vision of a future where we power our civilization without burning carbon or burying nuclear waste, effectively outsourcing our pollution to the barren surface of the Moon. Of course, this is a long-term horizon. We are not going to see lunar fusion plants next year. The reality is that we are still in the infancy of this industry. The cost of launching hardware is still astronomical, and the technology to mine and refine soil in a vacuum is unproven at scale. We are likely decades away from large-scale industrialization. The first steps will be robotic and tentative. Yet, the psychological shift has already occurred. The Moon is no longer just a light in the night sky. It is a destination with a business plan. While we look at the surface for resources, the Moon itself has been hiding a secret deep within its interior for generations. We were taught a simple model of lunar geology: a small core, a mantle, and a crust, all frozen and dead. We assumed that because the Moon is small, with a core making up only 1 to 2% of its total mass, compared to Earth's 30%, it must have cooled down completely eons ago. We thought of it as a solid block of stone. Recent data has shattered this assumption. Scientists analyzing data from lunar orbiters have discovered a hidden layer deep inside the Moon, a layer of what can technically be described as moon goo. It is a zone of soft, partially molten rock sitting at the boundary between the solid mantle and the core. This layer is not static, it is dynamic. It ebbs and flows, stretching and compressing in response to the gravitational pull of the Earth and the Sun. This discovery implies that the Moon is still, in a sense, alive. The interaction is mutual. Just as the Moon's gravity pulls on Earth's oceans to create tides, Earth's massive gravity pulls on this deep, molten layer inside the Moon, generating heat through friction. This tidal heating is likely what keeps this layer soft, preventing it from freezing solid despite the Moon's general coldness. The composition of this molten layer is equally fascinating. Leading theories suggest it is rich in a mineral called ilmenite. Ilmenite is a titanium iron oxide. If this deep layer is indeed a slurry of titanium-rich magma, it fundamentally changes our understanding of the Moon's resources. Titanium is a metal prized for its strength-to-weight ratio and its resistance to corrosion. While we cannot drill down to the core to harvest it, the existence of this layer suggests that titanium-rich lavas may have erupted to the surface in the past, depositing concentrated veins of ore that are accessible today. How did we find this hidden layer without drilling? We used gravity. The discovery was made possible by NASA's GRAIL mission, the Gravity Recovery and Interior Laboratory. The mission consisted of 2 washer-sized spacecraft named Ebb and Flow. They orbited the Moon in formation, flying one behind the other as they passed over mountains, craters, or dense underground structures. The slight changes in gravity would speed up or slow down the lead spacecraft, changing the distance between them by a fraction of a human hair. By constantly measuring this distance, scientists created a high-resolution map of the Moon's gravitational field. When combined with laser altimetry data from the Lunar Reconnaissance Orbiter, which maps the surface shape, they could subtract the topography to see what was happening underneath. The data revealed a rhythmic deformation of the Moon's interior that could only be explained by the presence of a soft, low-viscosity layer at the core mantle boundary. This goo layer solves several long-standing mysteries. It explains how the Moon dissipates tidal energy, and it offers a mechanism for some of the deep moonquakes that seismometers have recorded. It tells us that even small, cold worlds can maintain internal heat and geological activity far longer than we expected. It challenges our models of planetary evolution, suggesting that other moons and asteroids in our solar system might also be harboring hidden, molten hearts beneath their icy or rocky shells. From the molten depths, we turn our attention back to the shallow crust, where another geological wonder awaits: lava tubes. For over 50 years, scientists debated the existence of massive underground tunnels. We knew that on Earth, volcanic eruptions often create tubes when the surface of a lava river cools and hardens while the fluid rock continues to flow beneath. When the eruption stops, a hollow tunnel remains. Given the Moon's violent volcanic history evidenced by the vast basaltic plains of the Maria, it was logical to assume such tubes existed there as well. But proving it was difficult. We saw skylights, pits that looked like collapsed roofs, but we couldn't see inside. Now, using advanced radar and gravity analysis, we have confirmed their existence. These are not small caves, they are colossal. Because lunar gravity is 1/6 of Earth's, the roofs of these tunnels can support much more weight without collapsing. Some calculations suggest these tubes could be large enough to house a modern city, fully intact. These lava tubes represent the next frontier of exploration. They are time capsules, preserving the geological conditions of billions of years ago. More importantly, they are the perfect natural shelters. Inside a lava tube, the temperature is a constant, mild, 63 degrees Fahrenheit, regardless of the scorching day or freezing night on the surface. They offer instant protection from cosmic radiation and meteorite impacts. The first permanent human city on the Moon will likely not be built of domes on the surface, but will be tucked safely inside one of these ancient volcanic arteries. The molten heart of the Moon did not just churn in the deep, it shaped the very architecture of the crust we see today. Billions of years ago, when the Moon was young and violent, rivers of lava flowed across its surface. As these rivers moved, the outer layers, exposed to the vacuum of space, cooled rapidly and hardened into a crust of black rock. Beneath this solid roof, the hot, liquid lava continued to flow, insulated like water in a pipe. When the eruption finally ceased and the source drained away, it left behind empty, hollow tunnels. These are known as lava tubes. On Earth, we find these structures in volcanic landscapes like Hawaii, Iceland, and the Canary Islands. They are often tourist attractions, damp and dark. But on the Moon, the physics of gravity changes the scale completely. Because lunar gravity is only 1/6 that of Earth, the roofs of these tunnels can span miles without collapsing under their own weight. Lunar lava tubes are not just caves, they are cathedrals of the underworld, potentially large enough to house entire cities. For decades, these structures were theoretical. We saw long, winding depressions on the surface, called reels, that looked like collapsed tubes. But we couldn't see inside. That changed recently when an international team of scientists analyzed radar data from NASA's Lunar Reconnaissance Orbiter. They peered beneath the Sea of Tranquility, the historic site where Apollo 11 landed, and found a confirmed cave opening. It leads to a conduit at least 340 feet deep and potentially miles long. This is a game changer for human settlement. The surface of the moon is hostile. It is bombarded by micrometeorites, scorched by solar radiation, and subjected to wild temperature swings from boiling to freezing. But inside a lava tube, the environment is tranquil. The thick rock ceiling blocks the radiation and meteoroids. Most remarkably, thermal models suggest that deep inside these caves, the temperature remains a steady, comfortable 63 degrees Fahrenheit. Regardless of the time of day, it is a natural, ready-made habitat. If we can seal the entrances and pressurize the interior, we wouldn't need to build complex domes on the surface. We could simply move into the moon's own basement. There is also the tantalizing possibility of water. In the eternal darkness of these tubes, ancient ice might still cling to the walls, protected from sublimation. Exploring these depths will be the task of the next generation of robots, spiders that can rappel down cliffs or drones that can fly in low gravity, while the chances of finding life, even microbial, are infinitesimally small given the vacuum and lack of atmosphere. The exploration of these pristine environments will undoubtedly reveal geological secrets that have been protected from the weathering of space for eons. It is a race that is already beginning, with both the United States and China identifying these subterranean worlds as strategic targets for future bases. As we look up at the moon from Earth, we see a familiar face, the man in the moon, created by dark patches of ancient lava against a bright background. But have you ever wondered why we only see this one face? It is a phenomenon called tidal locking. The moon does rotate, but it rotates exactly once on its axis for every one orbit it completes around Earth. The dance is perfectly synchronized, keeping one hemisphere permanently turned away from us. We call this the far side. And until 1959, no human eye had ever seen it. When the Soviet probe Luna 3 beamed back the first grainy images, the scientific community was stunned. The far side looks nothing like the near side. The face we know is covered in Maria Vast, smooth seas of dark, basaltic rock. The far side, however, is a rugged, chaotic highland, densely pockmarked with craters and almost entirely devoid of those dark lava plains. It looks less like our moon and more like Mercury or Callisto. Why the difference? Why is the crust on the near side thin and flooded with lava, while the crust on the far side is thick and battered? This lunar dichotomy has been one of the longest-standing mysteries in planetary science. For years, researchers proposed the Earth's heat theory. It suggested that shortly after the moon formed, it was very close to a molten, glowing Earth. The intense heat radiating from our planet kept the near side of the moon molten for longer, preventing a thick crust from forming, while the far side, facing the cold of space, cooled and hardened rapidly. While elegant, This theory failed to explain the chemistry. The near side is not just thinner, it is chemically weird. It is home to a specific geological province known as the Prosolarum Creep Terrain, or PKT. This region is surprisingly rich in rare chemical elements, potassium K, rare earth elements REE, and phosphorus P, hence the acronym CREEP. These elements are heat-producing. They are radioactive. They act like a thermal blanket, keeping the mantle beneath them hot. The Earth's heat theory couldn't explain why all these radioactive elements decided to congregate on just one side of the moon. A competing theory suggested the moon once had a smaller twin, a second moon that eventually crashed into it, plastering itself onto the far side and creating the extra thick crust. But computer simulations showed that such a collision would likely be messier and wouldn't create the sharp distinction we see today. The answer, it seems, came from a different kind of violence. Recently, scientists analyzing gravity data from the Grail mission have coalesced around a new, dramatic explanation: a massive, ancient impact. About 4.3 billion years ago, a dwarf planet, roughly the size of Ceres, spanning 580 miles across, slammed into the moon near its south pole. This was not a small asteroid strike. It was a planetary collision. The impactor punched a hole in the crust, creating the South Pole Aitken Basin, the massive depression we discussed earlier. But the energy of the impact did something else. It sent a colossal shockwave rippling through the moon's interior. This shockwave, combined with the immense heat of the impact, triggered a massive convective flow inside the moon's mantle. It effectively pushed the layer of heat-producing creep elements, potassium, thorium, uranium, away from the impact site and concentrated them on the opposite side of the moon, the near side. This concentration of radioactive elements acted like a slow-burning stove. Over hundreds of millions of years, they generated enough internal heat to melt the mantle beneath the near-side crust. This caused massive volcanic eruptions. Lava poured out, filling the low-lying basins and craters, smoothing over the surface and creating the dark Maria that we see today. The far side, lacking this concentration of radioactive heat, cooled down, thickened, and preserved its ancient, cratered scars. So, when you look up at the moon tonight, you are not just seeing a rock, you are seeing the frozen aftermath of a cosmic car crash. The beautiful, smooth features of the near side are effectively the scar tissue of a wound inflicted on the other side of the world 4 billion years ago. This journey of discovery, from the microscopic grains of water-bearing dust to the continental-scale lava flows, reminds us that the moon is not a finished story. It is a dynamic world that has recorded the history of our solar system in its very geology. We have mapped its gravity, tasted its soil, and listened to its tremors. We have found water where there should be none, and heat where it should be cold. Now, we stand on the verge of returning, not just to visit, but to stay. We will likely build our homes in the lava tubes, mine the craters for the engines of the future, and peer back at the beginning of time from the quiet of the far side. The moon has been our companion, our calendar, and our muse for as long as humanity has looked up. Soon, it will be something else, our second home. The unraveling of the moon's history is far from complete. In fact, we are just beginning to read the most important chapters. For planetary scientists, the immediate future is defined by two specific targets on the lunar map: The first is the South Pole Aitken Basin, that colossal scar on the far side. Returning physical samples from this basin is the highest priority for robotic exploration. These rocks are expected to be pieces of the Moon's ancient mantle, excavated by the impact billions of years ago. By dating them, we can pinpoint the exact moment of the collision and refine our understanding of the violent epoch known as the Late Heavy Bombardment. The second target is the Muscovian Basin, a rare, large lava plain on the far side. It is an anomaly, a patch of dark mare in a land of bright highlands. Studying why lava flowed here, but almost nowhere else on the far side, will help us deconstruct the lunar dichotomy, explaining why the two faces of the Moon are so radically different. This is not just lunar history, it is solar system history. The Moon acts as a Rosetta Stone for cosmic time because it has no wind or rain to erase its craters. It preserves a record of every impact it has ever suffered. By counting these craters and correlating them with the age of rocks brought back by Apollo, scientists have built a timeline that we use to estimate the age of surfaces on Mars, Mercury, and even the moons of Jupiter. To understand the Moon is to understand the chronology of our entire celestial neighborhood. But as we study the past, the Moon is reminding us that it is not just a fossil, it is active. Imagine standing on the lunar surface, surrounded by absolute silence and stillness. You perceive it as a dead world, frozen in time. Then, without warning, the ground beneath your boots lurches violently. The vibrations travel through your suit, knocking you off balance. This is a moonquake, and it shatters the long-held myth that the Moon is geologically dead. For decades, the consensus was that lunar geological activity ceased over 1 billion years ago. However, startling new evidence from researchers at the University of Maryland and the Smithsonian Institution suggests otherwise. They have identified 266 mysterious ridges, scarps, and cliffs scattered across the far side. These are not ancient features eroded by time. They are sharp, crisp, and geologically fresh. These ridges are located in volcanic regions that formed more than 3 billion years ago. But the ridges themselves appear to be incredibly young, perhaps forming within the last 50 million years. In geological terms, 50 million years is yesterday. Some smaller features may be as young as 200 million years old. These discoveries imply that the Moon is still tectonically active today. It is creaking, shifting, and groaning. How do we know they are young? We use the crater counting method. On the Moon, older surfaces are densely packed with craters because they have been exposed to bombardment for longer. Younger surfaces have fewer craters. These ridges have very few craters superimposed on them. And in some cases, the ridges cut directly through small craters, proving that the fault movement happened after the crater was formed. This tectonic activity is driven by two powerful forces. The first is global contraction. As the Moon's core slowly cools over billions of years, it loses heat and shrinks. Because the crust is brittle, it cannot shrink smoothly. Instead, it buckles and breaks, thrusting one section of crust over another to create these wrinkle ridges and scarps. Essentially, the Moon is getting smaller, shriveling like a raisin as it dries out. The second force is the Earth. The gravitational pull of our planet does not just create tides in the moon goo layer we discussed. It exerts immense stress on the solid crust. These tidal forces massage the Moon, triggering fault slips and quakes, particularly when the moon is at the closest point in its orbit. The Apollo seismometers recorded 28 shallow moonquakes between 1969 and 1977, ranging up to magnitude 5. At the time, they were curiosities. Now, we realize they are warnings. This realization has profound implications for human settlement. We have spent years designing lunar bases under the assumption that the ground is stable bedrock. If the moon is prone to magnitude 5 earthquakes, our engineering needs to change. A quake of that size could rupture oxygen tanks, crack habitat seals, or destabilize landing pads. Before we pour concrete on the moon, we need a network of modern seismometers to map these fault lines and identify the safe zones. But the ground shaking is not the only hazard. The ground itself is a weapon. We return to the problem of regolith moon dust. This is not like the sand on a beach, which has been rounded by waves. Lunar dust is sharp, jagged, and abrasive, like microscopic shards of broken glass. Because the moon has virtually no atmosphere, there is no wind to tumble the particles and smooth their edges. Furthermore, this dust is electrostatically charged by the solar wind. It clings to everything: spacesuits, solar panels, camera lenses. During the Apollo missions, it clogged zippers, wore through the outer layers of spacesuits, and caused lunar hay fever in astronauts who inhaled it inside the lunar module. But in the era of mass exploration, the problem scales up. Researchers at Texas A&M have modeled the effects of rocket plumes. When a heavy lander touches down or takes off, its exhaust gases blast the surface, ejecting tons of this sharp dust at high velocities. In the vacuum of space, these particles travel for miles without slowing down. A single landing could effectively sandblast a nearby habitat or destroy delicate sensors on a rover parked miles away. Managing this dust building, landing pads with blast shields, or paving the surface is one of the most boring but critical challenges of lunar engineering. Yet, despite the quakes and the dust, the allure of the moon remains its resources, specifically water. The search for ice is intensifying. China is positioning itself at the forefront of this hunt with the upcoming Chang'e 7 mission, scheduled for roughly 2026. This ambitious mission plans to deploy a flying robot, a small probe capable of lifting off from the lander to hop into the deep, permanently shadowed craters of the South Pole. It will carry instruments to directly detect water ice. If confirmed, this ice changes the economics of space travel. It provides water for life support and hydrogen for fuel. It turns the moon from a destination into a gas station. But finding it is one thing. Extracting it in freezing darkness while surviving moonquakes and dust storms is another. It is a challenge that will define the next century of human exploration, as we reconsider the moon no longer as a dead rock, but as a dynamic, shrinking, quaking world with a hidden molten heart. Our eyes naturally drift further outward. If our own satellite can hide so many secrets, what about the other moons in our solar system? Take Mars. For example, the red planet is orbited by two small, lumpy moons, Phobos and Deimos. For a long time, they were dismissed as captured asteroids, boring rocks snagged by Mars's gravity. But recent observations of Phobos have revealed something strange. The surface of this potato-shaped moon is covered in long, straight grooves. Initially, Scientists thought these were fractures from a giant impact that nearly shattered the moon. But newer models suggest something far more dramatic. Phobos is falling apart. It is slowly spiraling closer to Mars, and the tidal forces are tearing it open. These grooves are the stretch marks of a moon in its death throes. Understanding these small worlds, whether it is the shrinking moon of Earth or the dying moon of Mars, reminds us that the solar system is not a static painting. It is a moving, evolving, and sometimes violent machine. We are just lucky enough to be awake to watch it happen. In the grand naming tradition of astronomy, celestial bodies often carry the weight of ancient mythologies. The planets are the gods themselves, and their moons are their attendants. Mars, the red planet, is named for the Roman god of war, Ares, in the Greek pantheon. It is fitting, then, that its two small satellites are named after the mythological sons of Ares, Phobos and Deimos. But these names are not merely labels. They are descriptions of the battlefield. Phobos means panic or fear, and Deimos means terror or dread. For centuries, these moons were just points of light, invisible to the naked eye and barely resolving in telescopes. It wasn't until 1971, when NASA's Mariner 9 spacecraft arrived at Mars, that we saw their true faces. The reality was a stark contrast to their terrifying names. They are not menacing worlds. They are lumpy, potato-shaped rocks, heavily cratered and gray. They look less like moons and more like cosmic debris that wandered too close. Phobos and Deimos are anomalies. They are the smallest moons in the solar system to orbit a major planet. Phobos is only about 14 miles across, and Deimos is even smaller. At roughly 8 miles, their orbits are equally strange. Phobos orbits so close to Mars, just 3,700 miles above the surface, that it completes 3 full orbits in a single Martian day. It races across the sky from west to east, setting twice a day. Deimos, on the other hand, drifts lazily in a much higher orbit. If you were standing on the Martian surface, the view would be underwhelming. Despite their proximity, they are so small that they fail to dominate the sky like our moon does on Earth. From the Martian equator, Phobos would look about 1/3 the size of our full moon, a jagged, irregular shape blotting out stars. Deimos would appear as nothing more than an exceptionally bright star, indistinguishable from a planet like Venus or Jupiter to the untrained eye. Because they orbit so close to the planet, the curvature of Mars actually hides them from the polar regions. If you built a base at the Martian North Pole, you would never see Phobos or Deimos rise above the horizon. But while they may look insignificant, Phobos, in particular, has become the center of a scientific detective story. When the Viking orbiters returned high-resolution images in the late 1970s, they revealed something disturbing. The surface of Phobos is scarred. It is covered in a network of deep, parallel grooves long, straight troughs that stretch across the moon like stretch marks. These are not small scratches. Some are nearly 1/2 mile wide and dozens of miles long. The existence of these grooves implies a violent history. Something happened to Phobos to crack its surface. For decades, scientists have debated 3 main theories to explain these scars, and the answer has implications for the future of the entire Martian system. The first suspect was the most obvious feature on the moon's Stickney crater. This is a colossal impact basin, named after Angeline Stickney, the mathematician and wife of Asaph Hall, who discovered the moons in 1877. The crater is 6 miles wide, nearly half the size of the moon itself. The impact that created it was so powerful it nearly shattered Phobos. It seemed logical to assume that the grooves were fractures created by the shockwave of this collision. However, forensic analysis of the images revealed a flaw. If the grooves were cracks from the impact, they should radiate outward from the crater like spokes on a wheel or cracks in a windshield. They don't. Many of the grooves run parallel to the crater rim or intersect at angles that have nothing to do with the impact site. The geometry simply doesn't fit the crime. This led to a second theory: space debris. This hypothesis suggests that Phobos has been repeatedly machine-gunned by rocks ejected from Mars. When a large meteor hits Mars, it blasts ejecta into orbit. Some of these rocks would intercept Phobos because Phobos has almost no gravity. These rocks wouldn't just land, they would graze the surface, rolling and bouncing, carving out long trenches before flying back off into space. This rolling boulder theory could explain why the grooves seem to form families of parallel lines. They trace the paths of debris clouds. It is a compelling idea, but it lacks physical evidence. If boulders carved these tracks, we should see the boulders stopped at the end of the tracks, or at least piles of rubble. But the grooves are clean. There are no massive boulders sitting at the ends of these trenches. The smoking gun is missing. This brings us to the third and most terrifying theory. The culprit isn't an asteroid or a rock. It is Mars itself. This theory posits that Phobos is a victim of tidal forces. Just as the moon pulls on Earth's oceans, Mars pulls on Phobos. But because Phobos is so close, spiraling inward at a rate of 6 feet every century, the gravitational differential is immense. The side of Phobos facing Mars is being pulled much harder than the far side. This differential is literally tearing the moon apart. The grooves we see are stretch marks, graben fissures opening up as the moon's internal structure fails. Phobos is not a solid rock. It is likely a rubble pile, a collection of rocks held together by gravity and a thin crust. As it gets closer to Mars, the tidal forces are overcoming its own weak gravity. This leads to a grim prediction. Phobos is doomed. In roughly 30 to 50 million years, it will cross a theoretical boundary known as the Roche limit. Once it crosses this line, the tidal forces from Mars will exceed the gravity holding the moon together. Phobos will not crash into Mars. It will disintegrate in midair. It will be ripped into billions of pieces, forming a dense ring of dust and rock around the red planet. For a brief period in cosmic history, Mars will look like a miniature Saturn, adorned with a ring made from the corpse of its own child. These grooves are the first cracks in the structural integrity of a dying world. Understanding the origin of these moons is a primary goal for the next generation of explorers. Are they captured asteroids from the main belt, snagged by Mars' gravity? Their composition, which resembles carbonaceous chondrite asteroids, suggests yes, but their orbits are circular and equatorial, which is nearly impossible for a captured object to achieve. Usually, captured moons have wild, elliptical orbits. This contradiction suggests they might have formed from debris blasted off Mars itself, meaning they are made of Martian crust. To solve this, the Japanese Aerospace Exploration Agency, JAXA, is preparing the MMX mission Martian Moons E-Exploration, scheduled to launch in the mid-2020s. This spacecraft will land on Phobos, collect a sample of its soil, and return it to Earth. If the soil matches Mars, we know they are children of the planet. If it matches asteroids, they are adopted strangers. While we wait for samples from the Martian moons, we have finally begun to decode the deepest secrets of our own moon. The question of what lies at the very center of the moon, its inner core, has been a subject of debate since the Apollo era. We knew the moon had layers, a crust, a mantle, and likely a core. But was the core solid, liquid, or a mix? And what was it made of? For years, the data was ambiguous. The Apollo seismometers provided a good look at the crust and upper mantle, but the signals from the deep core were too faint to interpret clearly. It was like trying to hear a heartbeat through a thick winter coat. However, in 2023, a team of French astronomers utilized a new technique to reanalyze decades of data. They used a method similar to how geologists study earthquakes on Earth, but enhanced with modern computer modeling. They looked at how the moon responds to the gravitational tides of the Earth and Sun, how it wobbles and deforms. By combining this rotation data with the old seismic profiles, they could effectively scan the interior. The results, published in the journal Nature, were definitive. The moon has a solid inner core. It is a ball of dense metal, roughly 310 miles in diameter. This inner core is surrounded by a fluid outer core, which explains the sloshing effects seen in the rotation data. Crucially, they calculated the density of this inner core. It is about 7,800 kilograms per cubic meter. To put that in perspective, that is almost exactly the density of pure iron. This finding is a massive victory for the giant impact hypothesis. It confirms that the moon's interior is remarkably similar to Earth's, yet distinct enough to suggest a shared, violent origin. Knowing that the moon has a solid, iron heart changes our understanding of its history. It implies that in its youth, the moon had a powerful magnetic field generated by the churning of its then molten core. This magnetic field would have protected the surface from solar wind, potentially allowing volatile chemicals like water to survive on the surface for longer than we thought. As the core cooled and solidified, the magnetic field died, leaving the moon exposed and barren as we see it today. This journey from the stretch marks on a dying Martian moon to the solid iron pulse of our own satellite demonstrates the power of modern planetary science. We are no longer just looking at shapes in telescopes. We are listening to the interiors of worlds, measuring their heartbeats, and predicting their deaths. The solar system is not a museum of static rocks. It is a dynamic, evolving engine, and we are finally learning how to read the gauges. To truly understand the moon, we must look beyond the surface scars and peer into the deep dark. For decades, the exact nature of the lunar core was a mystery. We knew it had gravity, but was it a solid rock, a slushy mix, or a molten ball? The answer came from a combination of seismic listening and a technique called lunar laser ranging. During the Apollo missions, astronauts placed retroreflector arrays, essentially high-tech mirrors on the lunar surface. For the last 50 years, scientists on Earth have been firing powerful lasers at these mirrors and measuring the time it takes for the light to bounce back. This measurement is incredibly precise, accurate to within a few millimeters. By tracking the minute wobbles in the moon's rotation, known as libration, scientists could deduce the density distribution inside. The verdict is in. The moon possesses a solid, iron-rich inner core, roughly 310 miles in diameter. This makes up about 15% of the moon's total diameter. Surrounding this solid heart is a fluid outer core and a partially molten boundary layer. This structure mirrors the Earth's own anatomy, reinforcing the deep familial bond between the two worlds. But the interior is not static. Evidence suggests that early in its history, the moon underwent a dramatic process called global mantle overturn. Imagine a lava lamp on a planetary scale. As the early magma ocean cooled, minerals crystallized. Ironically, some of the heavy, iron-rich minerals formed on top, while lighter magnesium-rich minerals stayed below. This configuration was unstable. Gravity eventually won, and the heavy layers sank catastrophically through the mantle toward the core, while the lighter material rose to the surface. This massive geological churning mixed the moon's interior and explains why we find surprising amounts of titanium and iron on the surface today. It was a planetary inversion that set the stage for the volcanic eruptions that would later paint the seas of the moon. This shared geology and iron core, a silicate mantle, brings us back to the ultimate question: where did the moon come from? The leading theory is violent and cinematic. It is known as the giant impact hypothesis. About 4.5 billion years ago, a protoplanet, roughly the size of Mars, named Theia, was on a collision course with the infant Earth. The impact was cataclysmic. It did not just dent the Earth, it liquefied the crust and blasted a massive cloud of debris into orbit. Within just 100 years, a blink of an eye in cosmic time, gravity pulled this debris ring together to form the moon. This explains why the moon is so large compared to Earth, a nickel next to a green pea, and why its rocks are almost identical to Earth's in their oxygen isotope composition. They are made of the same stuff. Other theories, like the capture theory, Earth grabbed a passing asteroid, or the fission theory, Earth spun so fast it threw off a chunk, fail to explain this chemical DNA match. For centuries, this shared origin story was complicated by one missing ingredient: water. The Earth is wet. The moon was thought to be dry. In the 17th century, astronomers looked at the dark plains and called them Maria, Latin for seas. They imagined waves and tides. By the late 1800s, telescopes revealed no clouds, and the dream of lunar oceans evaporated. The scientific consensus became rigid. The moon is a bone-dry desert, baked by the vacuum. But science is the art of correction. In 1961, physicist Kenneth Watson proposed a loophole. He suggested that in the deep craters of the poles, where the sun never rises, ice could hide forever in the shadows. For decades, this was just a theory. The Apollo samples were dry, but in the 1990s, orbital missions detected hydrogen. Then, in 2020, the Sophia Airborne Observatory detected the spectral fingerprint of water molecules on the sunlit surface, trapped inside glass beads or clinging to dust grains. We now know the water is there. It likely arrived via comets, dirty snowballs from the outer solar system bombarding the moon over billions of years. Or perhaps it is created by the solar wind itself, slamming protons into the oxygen-rich soil to manufacture water molecule by molecule. This water is not just a scientific curiosity, it is the fuel for our future expansion. It is the hydrogen for our rockets and the oxygen for our lungs. And then, there is the spectacle. The moon does not just reflect our history, Occasionally, it reflects our atmosphere. We call it a total lunar eclipse, or more dramatically, a blood moon. Here is the mechanics of the magic. The Earth orbits the Sun, and the Moon orbits the Earth. Occasionally, the three align perfectly, with the Earth in the middle. The Earth casts a long, cone-shaped shadow into space. When the Moon glides into this shadow, direct sunlight is cut off. You would expect the Moon to turn pitch black and disappear. Instead, it glows a deep, eerie copper red. Why? The answer lies in the Earth's atmosphere. Our atmosphere acts like a lens. It scatters blue light, which is why the sky is blue, but allows red and orange light to pass through and bend inward. This bent red light, essentially the light of every sunrise and sunset on Earth, happening simultaneously, is projected onto the Moon. If you were standing on the Moon during a lunar eclipse, looking back at Earth, you would see a terrifyingly beautiful sight. The Sun would be hidden behind the black disk of Earth. Surrounding the Earth would be a thin ring of fire, a glowing red halo of our atmosphere. The ground around you would be bathed in blood-red light. In ancient times, this sight caused panic. It was an omen of doom, a sign that the gods were angry. Christopher Columbus famously used a predicted eclipse to frighten indigenous islanders into supplying his crew. Today, we know better. We know it is a dance of orbital mechanics and atmospheric physics. But understanding the mechanism does not diminish the wonder. When we look up at the Moon today, we see more than a light in the sky. We see a sibling world, born from the same fire that forged Earth. We see a museum of the solar system's violent history. We see a treasure chest of resources waiting to be unlocked. And we see a destination. The Moon is no longer a distant god or a cold rock. It is the 8th continent. It is a place where the ground shakes, where ice hides in the shadows, and where the dust tells the story of 4 billion years. As we prepare to return not just to visit, but to stay, we are closing a circle that began when our ancestors first looked up and wondered. The Moon has been waiting for us. It is time to go back. Long before humanity looked up to admire the night sky, the story of the Moon began in fire. 4.5 billion years ago, the early solar system was a shooting gallery. It was a chaotic, violent place filled with dust, protoplanets, and massive asteroids playing a game of cosmic billiards. Our Earth was young, barely cooling from its own molten birth, when a shadow appeared on the horizon. It was Theia, a wandering planet roughly the size of Mars, spiraling inward on a collision course. The impact was inevitable, and when it happened, it was arguably the defining moment in our planet's history. Theia did not hit Earth head-on. A direct hit would have likely shattered both worlds, turning them into an asteroid belt. Instead, it struck at a perfect, glancing angle. The energy of the collision was unimaginable. It ripped off a massive chunk of Earth's crust and mantle, vaporizing rock into a cloud of superheated gas and dust. Theia was destroyed, its metallic core merging with Earth's, while the lighter debris was thrown into orbit. For a brief period, Earth had rings like Saturn, a glowing halo of molten rock. Over time, gravity did its work. This debris field began to clump together, accreted by its own gravity. until it formed the silver sphere we know today. This was not just a lucky accident. It was the lucky ticket for life. The collision did more than create a satellite. It tilted Earth's axis, giving us seasons. The moon's gravity stabilized Earth's wobble, preventing chaotic climate swings that would have made life impossible. Furthermore, the merger of the two cores likely supercharged Earth's magnetic field, creating the magnetosphere that shields us from deadly solar radiation to this day. Without that ancient crash, Earth might be as dead and barren as Mars. The relationship between Earth and Moon is dynamic. We are locked in a gravitational dance. The Moon pulls on Earth's oceans, creating the tides. Imagine the Earth as a ball of water. The Moon's gravity pulls the water toward it, creating a bulge, while centrifugal force creates another bulge on the opposite side. As the Moon orbits, these mountains of water travel around the globe. But this dance has a cost. The tidal friction is slowly stealing energy from Earth's rotation, pushing the Moon away. Every year, our satellite drifts about 1.5 inches farther into the dark. It is a slow farewell. In about 600 million years, the Moon will be so far away that it will appear too small in the sky to cover the sun. The spectacular phenomenon of a total solar eclipse will become a thing of the past, lost to history. The Moon's face bears the scars of its journey. One of the most prominent is the Tycho crater, easily visible from Earth during a full moon, as a bright navel with rays of ejected material stretching thousands of miles across the surface. This is a fresh wound. Scientists estimate Tycho formed about 109 million years ago. To put that in perspective, when that asteroid struck the Moon, dinosaurs were still roaming the Earth. A T-Rex, looking up at the night sky, might have witnessed the impact, a brilliant flash of light, and a silent explosion that looked like a celestial firework, marking the crust for eternity. Humans have always been drawn to these scars. We have sent robotic envoys and, eventually, ourselves. 12 human beings have walked on that gray dust. They discovered a world where the rules of movement are rewritten. The Moon has only 1/6 of Earth's gravity. A person weighing 180 pounds on Earth would tip the scales at just 30 pounds on the Moon, the weight of a medium-sized dog. This explains the strange, bounding gait of the Apollo astronauts. They weren't just walking, they were floating between steps. Conversely, their strength was magnified. On the Moon, an average human could lift weights that would be impossible on Earth, easily hoisting heavy equipment or, theoretically, a grizzly bear, if one happened to be there. But the most enduring mark we left is not the hardware, it is the footprints. The lunar surface is covered in regolith, a fine talcum powder, like dust produced by billions of years of meteorite impacts. This dust packs together perfectly to preserve shapes. The famous photo of a boot print is not just an image, it is a fossil of human technology. Interestingly, conspiracy theorists often point out that the print has ridges, while the astronauts' spacesuit boots were flat. The explanation is simple. Engineering astronauts wore jagged overshoes over their pressure suits to provide traction in the slippery dust. We left more than footprints. The landing sites are essentially museums. There are 3 lunar rovers parked in silence. American flags now likely bleached white by UV radiation. Scientific instruments. A golf ball hit by Alan Shepard. And yes, bags of human waste. In total, humanity has discarded about 400 13,000 pounds of material on the moon, the equivalent of 31 adult elephants. It is a testament to our presence, a mix of trash and treasure waiting for future archaeologists. The future of lunar exploration is shifting from visiting to staying. The next phase involves the Lunar Orbital Platform Gateway. Think of it as a space station, like the ISS, but orbiting the moon. This gateway will serve as a staging point. Launching a spaceship directly from Earth to deep space requires fighting Earth's massive gravity well, burning immense amounts of fuel. Launching from a lunar orbit, where gravity is weak, is far more efficient. It will be the gas station and harbor for ships heading to Mars and beyond. But to live there, we need resources, specifically water. We now know that ice exists in the permanently shadowed craters of the poles. Future rovers will not just take pictures, they will be miners, drilling down to extract this ice. If we can harvest it, we can separate the hydrogen and oxygen to make rocket fuel and breathable air. However, a colony faces a brutal enemy, the environment. The moon has no atmosphere to insulate it. Temperatures swing wildly, from boiling hot 250 degrees Fahrenheit in the day to freezing cold minus 200 degrees Fahrenheit at night. Worse, there is no shield against cosmic radiation. A house built on the surface would be a death trap. We would need to cover our habitats with thick layers of 3D printed regolith bricks, or better yet, go underground. This brings us back to the most exciting recent discovery: lunar caves. For years, we saw skylights, deep pits on the surface, but our cameras weren't good enough to see what lay beneath. Recently, scientists Leonardo Carrere and Lorenzo Bruzone from the University of Trento used advanced radar analysis on old data from the Lunar Reconnaissance Orbiter. They confirmed that these pits are not just holes. They are entrances to massive underground caverns. Specifically, in the Mare Tranquillitatis, they found a conduit leading into a stable lava tube. These tubes are remnants of the moon's volcanic past, formed when rivers of lava cooled on the top but kept flowing underneath, leaving behind empty tunnels. Some of these tubes are huge, hundreds of feet wide. They are nature's ready-made bunkers. Inside a lava tube, the temperature is a steady, mild 63 degrees Fahrenheit. The thick rock roof blocks the radiation and meteorites. Instead of building a base from scratch, future colonists might simply inflate a habitat inside one of these caves, sealing the entrance to create a pressurized, safe city beneath the surface. It sounds like science fiction, or perhaps a vacation brochure. Imagine a future space tourism industry, a 3-day flight from Earth, docking at the gateway, taking a lander down to the surface for a week of low-gravity hiking in the craters, and sleeping in a lava tube hotel. It is a long way from the red ball of lava that collided with Earth 4 billion years ago. But the path is being paved, one discovery at a time. The moon, once a creator of life on Earth, may soon become the second home for life in the solar system. While the surface of the moon is a landscape of extremes, oscillating between boiling heat and freezing cold, the underground offers a surprising sanctuary. Recent computer simulations suggest that inside the massive lava tubes of the Mare Tranquillitatis, the temperature remains a steady 63 degrees Fahrenheit. It is a perpetual spring, hidden beneath a world of gray desolation. This thermal stability changes the equation for colonization. Instead of heavy, power-hungry heating and cooling systems, A habitat inside a cave could be remarkably energy efficient. However, the engineering challenge shifts from how to survive to how to get there. The most promising cave entrance is a pit over 400 feet deep, with steep walls covered in loose, treacherous debris. We cannot simply rappel down. Future engineers are proposing concepts straight out of science fiction: lunar elevators to lower heavy equipment, or even cold gas jetpacks to allow astronauts to fly safely to the cave floor. Once inside, these explorers might find the most critical resource of all: water, in the permanent darkness of a cave. Ancient ice could be preserved in pristine condition, untouched for billions of years. Mapping these subterranean worlds is the next great frontier. Future missions will likely deploy swarms of drones equipped with ground-penetrating radar to create 3D maps of this underworld, identifying the safest locations for the first subterranean city. But before we build cities, we must remember how hard it was just to visit. The Apollo astronauts didn't just hop into a rocket. They spent years training in the most alien environments on Earth: the volcanic craters of Hawaii, the scorched deserts of Nevada, and the depths of the Grand Canyon, learning to identify rocks that tell the story of a planet. They practiced walking sideways, suspended in harnesses to simulate 1/6 gravity, learning a strange, loping gait to keep their balance. When Apollo 11 finally touched down in the Sea of Tranquility on July 20th, 1969, the experience was overwhelming. But one detail stands out in the astronauts' reports. Something you can't see in photos: the smell. When Neil Armstrong and Buzz Aldrin returned to the lunar module and took off their helmets, they noticed a pungent odor clinging to their suits. They described it as smelling like wet ashes in a fireplace or spent gunpowder. This is the smell of the moon. It is caused by the chemical reaction of moon dust with oxygen in the cabin. A sensory reminder that they had touched a truly alien world. Since that historic landing, only 12 humans have walked on the surface. They left behind more than scientific instruments. They left pieces of humanity. There are golf balls hit by Alan Shepard, a small silicon chip containing drawings by artists like Andy Warhol, and a message of peace from Queen Elizabeth II. Perhaps the most touching artifact was left by Eugene Cernan, the last man on the moon. Before leaving in 1972, he scratched the initials of his daughter, TTC, into the dust, because there is no wind or rain to erode them. Those 3 letters will likely remain there for millions of years, outlasting every monument on Earth. But the dust that preserves these memories is also a hazard. Astronaut Harrison Jack Schmitt discovered this the hard way during Apollo 17. After a moonwalk, he inhaled some of the fine dust floating in the cabin. Within minutes, his eyes became red and swollen, and he developed a sneezing fit that lasted for 2 hours. He was the first recorded case of extraterrestrial hay fever. The dust is silicate-rich and incredibly sharp. Inhaling it long-term could lead to serious lung conditions similar to silicosis in miners. Conquering this allergic reaction to the moon is a top priority for future suit designers. Time itself works differently there because the moon rotates so slowly. A day lasts about 29 Earth days. This makes tracking time confusing. Scientists have developed a lunar standard time, dividing the lunar year into 12 days, each named after an astronaut who walked on the surface. The calendar begins the moment Neil Armstrong's boot touched the soil. It is a symbolic system, reminding us that on the moon, We are the aliens trying to adapt. The moon also holds mysteries that science struggles to explain. For centuries, observers on Earth have reported strange flashes of light on the lunar surface, red glows, blue mists, or sudden sparks. These are known as transient lunar phenomena, or TLP. One of the earliest reports dates back to 1178, when monks in Canterbury described seeing the upper horn of the crescent moon split in two and spew fire. Modern science offers several theories. Some flashes are likely meteorite impacts, like the one the monks might have witnessed creating the Giordano Bruno crater. Others might be caused by outgassing pockets of gas trapped deep underground, suddenly escaping through cracks, reflecting sunlight or interacting with the solar wind to create a glow. The discovery of young fault ridges and seismic activity adds weight to the idea that the moon is not dead, but dormant, occasionally burping gas or shifting in its sleep, creating these ghostly lights. Sometimes, the moon changes color for us on Earth. We are used to the white or gray orb, but near the horizon, it can turn deep yellow or blood red due to atmospheric scattering. Rare conditions, like volcanic eruptions on Earth, throwing ash into the stratosphere, can filter the light to make the moon appear blue or even purple. These are atmospheric tricks, but they remind us of the intimate optical connection between our two worlds. As we look to the future, the Artemis program aims to rekindle our physical connection, but the stakes are higher now. We know that the radiation environment on the moon is brutal, about 200 times higher than on Earth, and 5 to 10 times higher than on a commercial flight. Artemis is not just about flags and footprints, it is about survival, scheduled to ramp up throughout the mid-2020s. Artemis will launch a series of increasingly complex missions. Artemis 1 will test the uncrewed Orion spacecraft. Artemis 2 will carry a crew around the moon, and Artemis 3, targeted for the middle of the decade, aims to land the first woman and the next man near the lunar South Pole. These astronauts will not just be tourists, they will be the architects of a permanent presence, laying the groundwork for the base that will one day harvest the ice, mine the soil, and perhaps welcome you to a hotel hidden safely inside a lava tube, where the smell of gunpowder and the view of a fragile blue Earth will change your life forever. The return to the moon is not merely an act of nostalgia, it is a rehearsal. The ultimate destination lies further out in the black void, drifting as a rusty red star in our night sky, Mars. The Artemis program, with its lunar space station and surface habitats, is designed as a technological crucible. It is where we will learn to solve the problems that would kill us instantly on Mars. But the leap from the moon to Mars is not just a matter of scale. It is a fundamental shift in the human experience. The moon is a 3-day journey away, a long weekend trip in cosmic terms. If an emergency strikes, home is just a radio call away. With a delay of barely 1.3 seconds, you can look up and see the Earth, massive and comforting, hanging overhead. A constant reminder that you are still in the neighborhood. Mars is different. It is a journey of 7 to 9 months. One way, the distance is so vast that radio signals take anywhere from 4 to 24 minutes to cross the gap. A conversation with mission control is impossible. Houston, we have a problem becomes a monologue. By the time Houston hears it, you are likely already dead or have fixed it yourself on Mars. The Earth is not a glorious marble. It is just a bright star in the morning sky, indistinguishable from Venus. The psychological impact of this Earth out of view phenomenon is one of the greatest unknowns of deep space travel, and the planet itself is a deceptive trap. Mars looks somewhat like Earth, with its canyons, volcanoes, and polar ice caps. It has a day-night cycle almost identical to ours, 24 hours and 37 minutes. But do not be fooled. Mars is a cold, radioactive desert. Its atmosphere is 95% carbon dioxide and 100 times thinner than Earth's. There is no ozone layer to block the sun's ultraviolet fury. The soil is laced with perchlorates, toxic chemicals that affect the thyroid. To survive here, we will need to master the technologies we are currently testing in the lava tubes of the moon closed-loop life support, radiation shielding, and in-situ resource utilization. The moon is the school, Mars is the final exam. However, if our goal is not just settlement, but the discovery of life, then perhaps neither the moon nor Mars is the most exciting target. As we gaze outward from our future lunar observatories, our attention may shift to the realm of the gas giants, Jupiter and Saturn. Here, huddled close to these massive planets, are the icy moons Europa, Ganymede, and Enceladus. These worlds shatter our conventional understanding of habitable zones. They are far outside the warmth of the sun, frozen in the deep cold of the outer solar system. Yet, they possess the one ingredient that defines life as we know it: liquid water. Much like the moon goo layer inside our own moon, these icy satellites are kneaded and stretched by the immense gravity of their parent planets. This tidal heating generates enough internal friction to melt the ice beneath their frozen crusts, creating vast, globe-spanning oceans of liquid water. Take Europa, one of Jupiter's moons. It is slightly smaller than our moon. Yet scientists believe its subsurface ocean contains twice as much water as all of Earth's oceans combined. Or consider Enceladus, a tiny moon of Saturn. It is actively venting plumes of water vapor and ice grains into space from cracks near its south pole. The Cassini spacecraft flew through these plumes and detected organic molecules, the chemical building blocks of life. While the moon is dry and geologically quiet, these ocean worlds are dynamic and wet. If life exists elsewhere in our solar system, it is likely swimming in the dark, warm depths of these alien seas, protected by miles of ice. The technology to drill through that ice and deploy submersible robots is being dreamed up today. Inspired by the drilling techniques we are perfecting to harvest ice at the lunar poles. This brings us back to the central question: why do we do it? Why spend billions of dollars to harvest dust on the moon or chase microbes on Enceladus when we face so many challenges here on Earth? The answer lies in a phenomenon reported by almost every astronaut who has ever left the atmosphere. It is called the overview effect. When you are on the surface of the Earth, your world is defined by borders, conflicts, and differences. You see nations, you see us versus them. But when you view the Earth from the moon, that perspective collapses. You see a fragile, blue sphere hanging in the emptiness, shielded by a razor-thin membrane of atmosphere. You do not see borders. You see a single, interconnected system, a lonely spaceship carrying all the life we have ever known. Going to the moon does not distract us from Earth's problems. It puts them in sharp focus. The environmental technologies developed for space-efficient solar panels, water purification systems that recycle every drop, and vertical farming are exactly the tools we need to solve climate and resource challenges on Earth. The satellites we launch to study other worlds also turn their sensors back on us, monitoring deforestation, melting ice caps, and storm patterns with unprecedented precision. Furthermore, space exploration is an insurance policy. The geological history of the Moon teaches us a violent lesson: giant rocks fall from the sky. The craters that pockmark the lunar surface are records of impacts that, had they hit Earth, would have ended civilization. By mastering space travel, by building telescopes on the lunar far side to track asteroids, and by learning to deflect them, we are protecting our home from the inevitable cosmic shooting gallery. As we stand at the dawn of this new era, looking up at the Moon, we are no longer just passive observers. For thousands of years, the Moon was a god, a calendar, a source of light, and a destination for our dreams. It has watched over the evolution of life on Earth, pulling our tides and stabilizing our seasons. Now, the relationship is changing. We are crossing the void to meet it. We will return to the Sea of Tranquility, not just to visit the museum of Apollo 11, but to live. We will mine the resources of the South Pole to fuel our journey to the stars. We will build observatories in the silence of the far side to listen to the whispers of the Big Bang. And in the process, we will become a multi-planetary species. The journey that began with a single footstep in the gray dust of 1969 is far from over. In fact, the true voyage is just beginning. The Moon is waiting, Mars is calling, and the infinite dark beyond is filled with questions that we finally have the courage to answer.